Welcome to chemistry classes. In this video we are going to discuss about electrons in an atom. Electrons in an atom. A-level chemistry chapter 3. We know atoms. Atoms are the smallest part of any matter. In the middle of atom there is very hard and tiny center. This hard and tiny center, it is called nucleus. Inside nucleus we can see neutron and proton. Around nucleus there are circular path. In circular path we can find electrons. We can find electrons in circular path around nucleus. This circular path is called orbit. This circular path is called orbit or energy level. Energy level or orbit. Also it is called principal energy level. Principal energy level. It is numbered like this. 1, 2, 3. Here principal energy level it is represented by N. Principal energy level represented by N and it is numbered 1, 2, 3. Number 1 means this is first orbit. First orbit, it is very close to nucleus. Okay. And 1, 2, 3 and it's going on, and the last orbit it will be very far from nucleus. Also we have to understand here each orbit they have particular energy. Here this is first orbit, second orbit, third orbit or energy level. Each energy level they have fixed energy. Energy of orbit close to nucleus they have lower energy. Okay, look here, this is first orbit. First orbit it is very close to nucleus, it has lower energy. Orbit or energy level far from nucleus has less energy. Okay, here you can arrange this orbit according to their energy. Here first orbit less energy than second orbit less than third, etc. Okay, so energy level far from nucleus less energy, energy level close to nucleus higher energy. Clear? So these are the things we have to discuss here. Next point we have to discuss here electronic structure. Electronic structure. Electronic distribution. Electronic distribution or distribution of electron in each orbit. It is called electronic configuration or electronic structure. Distribution of electrons in each orbit, it is termed as electronic structure or electronic configuration. See here some example here. Lithium, we know lithium atomic number 3. So first shell 2 electron, second shell 1 electron. Neon atomic number 10. First orbit 2 electron, second orbit 8 electron. Similarly chlorine 17. 287. Okay, look here another example here. Potassium atomic number 19. So first orbit how many electron? 2 electron, second 8, third one again 8, then 1. Okay, 2, 8, 8, 1. Look here another example. Calcium atomic number 20. So first orbit how many electron? First orbit 2 electron. First orbit 2 electron. Second orbit 8. Again 8. Now how many electrons here? 2, 8, 8. It is 18. We have total 20 electron. How many electrons left? Here 18. 18 minus 20, 2 electron less. So this is the electronic structure of calcium. Okay, next one we have to discuss here evidence for electronic configuration. Evidence for electronic configuration. Evidence for electronic configuration is ionization energy. Ionization energy and successive ionization energies are the evidence for electronic configuration. We discuss first shell 2 electron, second shell 8 electron, third shell again 8, okay, so on. So this type of electronic configuration here, ionization enthalpy or successive ionization enthalpy gives information about this type of electronic configuration. Okay, so see here, here it is one gaseous atom, gaseous atom. After firing a high speed electron to a gaseous atom, it is possible to measure amount of energy required to remove an outer shell electron from a gaseous atom, and then this gaseous atom changes to gaseous ion. The amount of energy required to remove outer shell electron of a gaseous atom to change gaseous ion, this amount of energy called ionization energy. Ionization energy means amount of energy required to remove outer shell electron. Outer shell electron, imagine you have one atom, okay, imagine there are many shell, you want to remove this outer shell electron from this gaseous atom. This is 1 mole atom, 1 mole gaseous atom, we want to remove outer shell electron. After removing this outer shell electron, this atom will change to gaseous ion. Gaseous atom changes to gaseous ion. 1 mole gaseous atom, after removing 1 electron, it changes to 1 mole gaseous ion. Amount of energy required for this process, it is called ionization energy. There is first ionization enthalpy. You can say ionization energy or ionization enthalpy. Ionization energy or ionization enthalpy. Okay, so there is first ionization enthalpy, second ionization enthalpy, third ionization enthalpy, and so on. Okay, first ionization enthalpy, actually ionization enthalpy represented by delta Hi. Delta Hi mean ionization enthalpy. Also this one delta H, this represent standard enthalpy, standard ionization enthalpy. Standard ionization enthalpy mean this process takes place at the standard condition 25 degrees Celsius and 25 degrees Celsius and 1 atmospheric pressure, 25 degrees Celsius or 298 Kelvin and 1 atmospheric pressure. That is standard condition. Okay, so here this is ionization enthalpy. So this ionization enthalpy, there is first ionization enthalpy, second ionization enthalpy, third ionization enthalpy. First ionization enthalpy mean amount of energy required to remove first outer shell electron. First outer shell electron of a 1 mole gaseous atom, and then it changes to 1 mole gaseous ion. Amount of energy required for this process, it is first ionization energy. Second ionization energy or second ionization enthalpy mean amount of energy required to remove second outer shell electron of 1 mole gaseous atom. 1 mole gaseous atom, okay, we already removed 1 electron. Then again we want to remove second outer shell electron. Amount of energy required for this process, it is called second ionization energy. Look here, this is one example for first ionization energy, second ionization energy, third ionization energy equation. Here we have calcium. Calcium, it is gaseous state. Okay, here 1 mole gaseous calcium. We know calcium, it is solid state after sublimation. Okay, after sublimation we have to change calcium in vapor state or gaseous state from 1 mole gaseous calcium, we remove electron and it changes to one more gaseous calcium ion. Amount of energy required to remove one electron, first outer shell electron from gaseous calcium, it is 590 kilojoule per mole. Okay, so this is first ionization energy. After removing first outer shell electron, gaseous calcium changed to gaseous calcium ion. Okay, Ca plus. We removed one electron, so it is Ca plus. From gaseous Ca plus, again we removing second outermost electron. Okay, amount of energy required for this process, it is called second ionization enthalpy. So second ionization enthalpy mean amount of energy required to remove second outermost shell electron of one mole gaseous atom, then it changed to one mole gaseous ion. Okay, look here, after second ionization enthalpy, calcium changed to gaseous calcium 2 plus. From gaseous calcium 2 plus, we have to remove one more electron, then it changed to gaseous calcium 3 plus. Amount of energy required for this process, it is third ionization enthalpy. First ionization enthalpy, second ionization enthalpy, third ionization enthalpy. Okay, so here in calcium, first ionization enthalpy 590. Then it is 1150. Then it is 4940. First ionization enthalpy for calcium, it is 590. Second ionization enthalpy 1150. Third ionization enthalpy 4940. So this sequence showing that first ionization enthalpy, look here, delta H1 is less than delta H2. Okay, delta H1 less than delta H2, it is less than delta H3. So here this showing that third ionization enthalpy is greater than, second ionization enthalpy is greater than first ionization enthalpy. Okay, so here imagine this is nucleus. Okay, so these are different electron. Imagine this is outer shell electron. After removing this electron, next outer shell electron is much close to nucleus. So attraction between nucleus and outer shell electron will be stronger and it need more energy. Okay, so this is second ionization energy, it removed. Then next third outer shell electron, it is much more close to nucleus. So attraction between nucleus and the outer shell electron will be more stronger and we have to give more energy. Okay, so here this is the first outer shell electron. Okay, first ionization enthalpy mean amount of energy required to remove first outer shell electron. So here this electron is comparatively far from nucleus, less attraction between nucleus and outer shell electron, and we can remove electron very easily. After removing first outer shell electron, second outer shell electron, it is close to nucleus compared to first outer shell, second outer shell electron close to nucleus. Okay, I showed here, this is nucleus. Okay, these are different electron. This is first outer shell electron, it is far from nucleus. After removing this electron, next outer shell electron, it is close to nucleus. After removing this electron, third outer shell electron much more close to nucleus. Okay, so attraction between nucleus and outer shell electron will be more and it need more energy to remove this electron. Okay, and this sequence of successive ionization energy, it is called successive ionization energy. Okay, this step by step removal of electron. Okay, we can remove electron from an atom until nucleus left. We can remove electron by step process until nucleus left. I showed here before there was many electron. We removed this electron. This is first ionization enthalpy. After that we removed this electron. This is second ionization enthalpy. Again we removed this electron. Third ionization enthalpy. Fourth ionization enthalpy. Finally there is nucleus only. Okay, so this step by step removal of electron from an atom, okay, gaseous atom, this removal of electron, it is called successive ionization enthalpy. So successive ionization enthalpy energy order like this. Okay, the first ionization enthalpy is less than second ionization enthalpy. It is less than third ionization enthalpy, then fourth ionization enthalpy. Because first ionization enthalpy, electron is far from nucleus, so it needs less energy to remove this electron. Okay, then second outer shell electron, it is much close to nucleus, more attraction between nucleus and outer shell electron. We have to give more energy. So ionization enthalpy increases. Okay, so here we discuss successive ionization energy. Successive ionization energy, first ionization energy less than second ionization energy less than third ionization energy. Okay, so when we are going very near to nucleus, attraction between nucleus and the outer shell electron will be much stronger, and we have to give much more energy to remove outer shell electron. Okay, so look here, these are the successive ionization energy of nitrogen and sodium. Successive ionization energy of nitrogen and sodium. Okay, this is first ionization energy or first ionization enthalpy, second ionization enthalpy, third ionization enthalpy, etc. These are successive ionization energy of sodium. First ionization energy, second ionization energy, third ionization energy, etc. Okay, so you can see here first ionization energy, it is 494. Second ionization energy 4560. Third ionization energy 6940. So here first ionization energy less than second ionization energy less than third ionization energy. Okay, so from this type of successive ionization energy we will get many information. Okay, so look here, in case of sodium, this is first ionization energy. Okay, and this is second ionization energy. So here you can see a big difference, a big jump in ionization energy from first ionization energy to second ionization energy. Okay, first ionization energy, it is 494. Okay, and here second ionization energy, it is 4560. So you can see a big difference. So this type of big difference indicate that the first electron in one energy level and second electron, okay, this electron in one energy level and this electron in another energy level. We know what is energy level. Okay, we discuss first nucleus energy level, first energy level, second energy level, third energy level, etc. Okay, so in case of sodium, here first outer shell electron, amount of energy required to remove first outer shell electron. This is first ionization energy, and this is second ionization energy. When we observe this data, there is a big difference. It indicates that first electron in one energy level and second electron in another energy level. Okay, that's why here a big difference in their energy level. Okay, this electron is far from nucleus. Okay, so less attraction between this electron and nucleus and less amount of energy needed to remove this electron. But when we consider second outer shell electron, it is another energy level, and this energy level is close to nucleus. This compared to first outer shell electron energy level, second electron energy level is close to nucleus, and much more attraction between this electron and nucleus, and we have to give much more energy. Okay, so this type of big difference indicate that the electrons are in different energy level. Clear? So look here, this is 494. After that, here first, after that second, third, fourth, fifth, sixth, seventh, and eighth. Okay. So here after first ionization energy, when you compare these values, they are much closer. These values are closer. There is no big difference. Okay, here 494, here 4560. There is a big difference. So these electrons are in different energy level. But when you consider rest of the ionization enthalpy from second ionization enthalpy to 8th ionization enthalpy, these values are much close. It indicates that these 8 electrons are in same energy level. Okay, here big difference mean energy levels are in different energy level, but this 8 ionization energy, there is no big difference. It indicates that these 8 electrons are in same energy level. Okay, so here we discuss this is ionization energy of sodium. Here you can see a big difference in first ionization energy and second ionization energy. Okay, then rest of the ionization energy, there is increase. Ionization energy increases from second, third, fourth, but these values are close each other. Okay, after that last two ionization energy, we can observe that there is a big difference. Okay, compared to 8th ionization energy, last two ionization energy, we can observe a big difference, a big increase. Okay, so it indicates that last two electrons also in another energy level. That energy level, it is much more close to nucleus. So this graph indicates that ionization, log ionization energy and number of electrons. Okay, so here ionization energy increases from bottom to top. Ionization energy increases, and this is number of electrons. Look here, this is first outer shell electron, second outer shell electron, third, fourth, fifth, etc. So this graph indicates sodium. Okay, 1 2 3 4 5 6 7 8 8 9 10. Okay, here 1 2 3 4 5 6 7 8 9 10 11. We know sodium, there is 11 electron. So here 11 electron. I told you in the beginning, here this is first ionization energy, first ionization energy and second ionization energy, there is a big difference. After that, this is last two electron. Also we can observe here a big increase in ionization energy. It indicates that first ionization energy, first outer shell electron, it is in one orbit. Another 8 electrons are in another orbit, and last two ionization energy, these 2 electrons are in another energy level. So this successive ionization energy indicate that sodium consists of three energy level, three principal energy level. Okay, so similarly this is nitrogen. Okay, so these are the different ionization energy values of nitrogen. Okay, and here this is first ionization energy, second, third, fourth, fifth. Okay, so this 5 ionization energy, 5 successive ionization energy, these are different from last 2 ionization energy. This 5 successive ionization energy, there is increasing. You can see one first ionization energy. First 5 successive ionization energy, it increasing. Okay, but last 2 ionization energy, there is a big increases. First 5 ionization energy, there is increasing, but these values are close each other. But last 2 ionization energy, there is a big difference. Okay, it indicates that this first 5 electrons are in one energy level and last 2 electrons are another energy level. So nitrogen consists of 2 main energy level. Okay, here 2 electron in one energy level and 5 electrons are in another energy level. So atomic number of nitrogen 7. So there is 2 energy level, and first energy level 2 electron, second energy level 5 electron. Okay, so this type of successive ionization energy, it helps us to find different number of energy level in a given atom. Okay, so this type of big difference indicate that electrons are in different energy level. Clear? Okay, next one we have to discuss here factors which influence ionization enthalpy. Different factors which influence ionization enthalpy. Okay, so here first one we have to check here effective nuclear charge, size of effective nuclear charge. We know from left to right in periodic table, from left to right, number of protons increases, atomic number increases, so number of protons increases. So number of protons increases mean positive charge of nucleus increases, effective nuclear charge increases. Effective nuclear charge mean the positive power of nucleus increases from left to right in a periodic table. So attraction between nucleus and outer shell electron increases. Nucleus positive charge, electrons are negative charge. Okay, so effective nuclear charge increases mean attraction between nucleus and outer shell electrons increases. So we have to give much more energy. We have to give more energy to remove outer shell electron. Okay, that is effective nuclear charge. Effective nuclear charge mean as proton number increases, number of protons increases, positive power of nucleus also increases. That's mean effective nuclear charge of an atom increases. So attraction between nucleus and outer shell electron will be increases, and we have to give much more energy to remove outer shell electron. Okay, so here generally you understand effective nuclear charge increases, ionization enthalpy increases. Clear? After that, we have to understand here second factor, distance between outer shell electron and nucleus. Distance between nucleus and outer shell electron. This distance. Okay. We know nucleus, it is positively charged and electrons are negatively charged. Okay. Imagine this is one atom and here this is outer shell electron. Amount of energy required to remove this electron, that is ionization enthalpy. Okay, positively charged nucleus and negatively charged electron, there will be attraction. So distance between nucleus and outer shell electron increases mean less attraction between nucleus and outer shell electron. Less attraction means less energy required to remove outer shell electron. So ionization enthalpy decreases. So second factor to depend ionization enthalpy, distance between nucleus and outer shell electron. Okay, less distance between nucleus and the outer shell electron, much more attraction, ionization enthalpy increases. Okay, more distance between outer shell electron and nucleus mean we have to give more energy to remove outer shell electron. Okay, so here third factor, shielding effect of inner electron. Look here, this is, imagine this is one atom, this is nucleus. Okay, this is outer shell electron, nucleus and outer shell electron. Between nucleus and outer shell electron there are many orbits. These orbits are called inner orbit or inner shell. Okay, electrons present inner shells are called inner shell electron. So see here, this is nucleus and this is orbit. Between this outer shell electron and nucleus there are many orbits and there are many electrons. We know electrons, they have negative charge. There are many electrons and these electrons have negative charge and these electrons will repel each other. This repulsion called inner electronic repulsion, inter-electronic repulsion. Okay, this repulsion between electrons present inside this orbit, it is called inter-electronic repulsion. Clear? This inter-electronic repulsion. So if there is much more inter-electronic repulsion, this electron will repel. Repel means it try to stay away from nucleus because there is repulsion between this electron and rest of the electron. So this outer shell electron try to stay far from nucleus and there will be less attraction between nucleus and outer shell electron. So we can remove this outer shell electron easily. So ionization enthalpy decreases. So here shielding effect. Shielding. Why we called shielding? Because here this inner electrons make a shield between nucleus and the outer shell electron. This inner electron act as a shield between nucleus and the outer shell electron. That's why we call shielding effect. Shielding effect means inner electrons, number of inner shell electrons increases, electron repulsion will be there and the outer shell electron try to stay maximum away from nucleus and the attraction between nucleus and the outer shell electron will be less or decreases and amount of energy required to remove this electron will be decreases. Next one, we have to discuss here trend in ionization energy. Okay, when we move from left to right in a period, what happened to ionization energy? When you are going from top to down in a group, what happened to ionization energy? These are the things we have to discuss here. Trend in ionization energy. Look here, group mean from top to down, it is group. Okay, example here, first group element lithium, sodium, potassium, rubidium, cesium, francium. Lithium here, you know, from top to down atomic number increases. Atomic number increases from top to down. Atomic number increases, also size of the atom increases. Size of the atom increases from top to down. Size of the atom increases mean distance between nucleus and outer shell electron increases. Distance between nucleus and outer shell electron increases. We discussed already. Distance between nucleus and outer shell electron increases mean attraction between positively charged nucleus and negatively charged electron decreases. So we can remove outer shell electron very easily and ionization energy decreases. Okay, so ionization energy decreases from top to down. Also another reason, shielding effect. Number of electrons increases mean number of inner shell electrons also increases. Atomic size increases from top to down. Also number of shells increases. Number of inner shell increases. Also number of inner shell increases mean number of inner shell electrons increases. Number of inner shell electrons increases. So inter-electronic repulsion increases. That's why ionization energy decreases. So there are two reasons to decrease ionization energy from top to down. First reason, atomic size increases, distance between nucleus and outer shell electron increases, so less energy required. Second reason, shielding effect. Number of inner shell electrons increases, so electron repulsion increases. Outer shell electrons stay maximum away from nucleus, so less energy required to remove outer shell electron. These are the reason for decreasing ionization energy from top to down. For example, from lithium to francium. Clear? Next one here we have to discuss in period. Period means from left to right in a periodic table, that is period. Example for period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Lithium atomic number 3. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So lithium atomic number 3, 4, 5, 6, 7, 8, 9, 10. Atomic number increases from left to right in a group, in periodic table. Atomic number increases mean number of protons increases. Number of protons increases. So number of protons increases mean effective nuclear charge increases. Effective nuclear charge increases. Attraction between nucleus and outer shell electron increases. Okay, so effective nuclear charge increases mean much more attraction, or attraction between nucleus and outer shell electron increases from lithium to neon. So generally ionization energy increases from left to right. There are exception case we will discuss later, but generally we can say ionization energy increases in a period from left to right. Okay, because effective nuclear charge increases. This is one reason. From left to right in a period ionization energy increases. What is the reason? First reason, effective nuclear charge increases. Second reason, less shielding. Okay, look here, you can check here atomic number 3, 4, 5, 6, 7, 8, 9, 10. So here first shell, here first one, 2, 1, 2, 2, 2, 3, 2, 4. These are the electronic structure. Electronic structure here 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. So there is number of shells not increases. Number of shells not increasing. Okay, but the charge, positive charge of nucleus increasing. So there is shielding effect not increasing, same like this, shielding effect not increasing here, okay, but effective nuclear charge increases. That's why in period ionization energy generally increasing from left to right. Clear? After that, we have to understand here uses of ionization energy. Last point in this video, we have to discuss here ionization energy, uses of ionization energy. So in this video, we discussed electrons in an atom, okay, energy level, electronic structure, okay. After that, evidence for electronic structure, ionization enthalpy, first ionization enthalpy, second ionization enthalpy, successive ionization enthalpy, and also we discuss log ionization energy against number of electron graph, okay. From this graph we can interpret different energy level, number of energy level in an orbit, okay. These things already we discussed, you can review these things, okay. And sorry, here last point in this video, we have to discuss here uses of ionization energy, okay, uses of ionization energy. This ionization energy helps to predict simple electronic structure. Ionization energy helps to predict simple electronic structure. Also, ionization energy helps to find number of outer shell electron. Also, it helps to find the group in a periodic table. Okay, so these are the some uses of ionization energy. Ionization energy helps to predict simple electronic structure, okay. Also, it helps to find number of electrons in outer shell. With help of number of electrons in outer shell, it is able to find group in a periodic table, okay. So these are the different uses of ionization energy. So these are the things we have to discuss in this video. Rest of the things we will discuss next video, okay. So thank you for watching this channel.